Imagine you are holding a flashlight. The light leaves the bulb at the absolute speed limit of the universe, nearly 300,000 kilometers per second. But what happens if you turn that flashlight on while riding inside a rocket ship that is moving at half that speed? Intuition suggests the light should get a boost from the rocket. Albert Einstein argued otherwise. In this portrait of the physicist, we are reminded of his second postulate of special relativity. He stated that the speed of light, represented by the letter c, remains strictly constant for everyone, regardless of how fast the light source is moving. Speed is simply distance divided by time. If the speed of a light beam is locked in place, but the distance it travels appears to increase from the perspective of an outside observer, the equation still has to balance. The only remaining variable is time. Time itself has to stretch. To see exactly how that happens, we can construct a thought experiment. This animation shows a light clock. It consists of a bottom mirror, a top mirror, and a single photon of light bouncing between them. The distance between the mirrors is exactly L. We define one complete tick of this clock as the time it takes the photon to travel up to the top mirror and bounce back down to the bottom. That total round-trip distance is simply L plus L, or 2L. Using the basic formula that time equals distance divided by rate, we can calculate the duration of that tick. We take our total distance, 2L, and divide it by our constant rate, the speed of light, c. That gives us our baseline equation, delta t equals 2L over c. This represents the passage of time when the clock is completely at rest relative to us. Keep this baseline in mind. We are going to compare it to a clock that is moving. Now let's change our perspective. This animation shows that same light clock, but now we are watching it glide to the right at a constant velocity, which we'll call v.
Because the clock is moving forward while the photon bounces up and down, that photon is now tracing a wide, diagonal zigzag path. Your brain naturally wants to compensate for this. It feels like the forward velocity of the clock should be added to the speed of the photon, helping it cover this new, longer diagonal distance in the same amount of time. But Einstein's rule forbids that. The speed of the photon along that elongated diagonal path remains exactly c. It doesn't get a speed boost from the moving clock. The photon is covering a significantly longer physical distance, and it is doing so at the exact same speed limit. Therefore, the duration of this tick must be longer. We will call this stretched moving time delta t prime. To calculate exactly how much longer that moving tick takes, we need to translate the physics into geometry. Here, we freeze the animation exactly halfway through a tick, right as the photon strikes the top mirror. By laying a right triangle over the path, we can define the distances involved. The vertical leg of our triangle is the height of the clock. We already established that light travels this height in half the resting time. So this leg is equal to the speed of light, c, multiplied by our resting time divided by 2. During that exact same half tick, the clock itself moved forward. The base of the triangle is that horizontal distance. That equals the clock's velocity, v, multiplied by the moving time, delta t prime, divided by 2. Finally, the hypotenuse is the diagonal path the photon actually traveled. That equals the strict speed of light, c, multiplied by the moving time, delta t prime, divided by 2. We now have a right triangle with all three sides defined algebraically. Pause the video here, grab a piece of paper, and use the Pythagorean theorem, a squared plus b squared equals c squared, to combine these three sides into a single equation. Here is the Pythagorean setup. Squaring the bracketed terms reveals a shared denominator of 4, which we cancel. To isolate delta t prime, we subtract the v squared term and move it right. Factoring out delta t prime squared cleanly separates resting time from moving time. Dividing both sides isolates delta t prime squared. Simplifying leaves 1 minus v squared over c squared on the bottom. The square root provides the time dilation formula. Since velocity is less than light speed, this denominator, the Lorentz factor, gamma, is less than 1, guaranteeing moving time is larger. This 3-panel graphic summarizes our proof. We defined how a stationary clock measures time, mapped the elongated geometry of a moving clock, and solved the algebra to prove that for any moving object, time itself must strictly pass more slowly. This diagram sets up our physical scenario. On the left, we have a stationary observer holding a clock, which we'll call frame S. On the right, we have a second observer flying past in a spaceship at a constant velocity, representing frame S prime.
To translate time measurements between these two frames of reference, we rely on the Lorentz time transformation. You don't need to learn a completely new system of physics to see how this works. By following the basic algebra of this one equation, the reality of time dilation naturally proves itself. In physics, a specific moment in time and space is called an event. To figure out how our moving observer perceives the stationary clock, we need to track two specific events: Event A, the clock's first tick, and Event B, the clock's second tick. Here, we see the Lorentz equation mapped specifically to that first tick. The observer's time for Event A, t prime sub A, is calculated using the time and position in the stationary frame. Right below it, a second equation for Event B represents the clock's second tick with its own distinct coordinates. With these two formulas in place, we now have a complete mathematical representation of how the observer in the speeding spaceship perceives the start and the end of a single clock tick. But before doing any calculations, look closely at the numerators. Both equations contain a complex spatial variable, x sub A and x sub B. Remember the physical reality of the clock we are measuring. Because it sits entirely at rest in its own frame, the first tick and the second tick happen at the exact same physical location. Looking at these highlighted variables, the mathematical consequence of being at rest is clear. The spatial coordinate for Event A must perfectly equal the spatial coordinate for Event B. This condition simplifies the algebra, allowing us to strip away the spatial variables and focus purely on the temporal relationship between the two observers. To find the dilated time interval for the moving observer, which we'll denote as delta t prime, we subtract the time of Event A from the time of Event B. This full expanded equation shows what happens when we substitute our two bulky Lorentz fractions into that subtraction problem. We've highlighted the temporal terms in blue and the spatial terms in red. Pause and look closely at the red spatial terms across that subtraction sign. Keep in mind our co-local condition, x sub A equals x sub B. Because we are subtracting the entire second fraction, the double negative turns the second spatial term positive. That positive spatial term from Event A is perfectly canceled by the negative spatial term from Event B. Because the clock didn't move through space in its own frame, all spatial dimensions cancel out of the math entirely. We are left to deal purely with the flow of time. Look at the drastically simplified numerator, t sub b minus t sub a. This represents the actual time interval between the two ticks as measured by the clock sitting in its own rest frame. In physics, this is called proper time. We substitute the symbol delta t into the numerator to replace those two original variables. Next, we isolate that bulky square root denominator and replace it with the standard symbol for the Lorentz factor, gamma, revealing our final elegant formula. Because the Lorentz factor is always greater than 1, the resulting math shows that the moving observer's time interval, delta t prime, must be stretched compared to the proper time. This summary card outlines the 4 critical steps we took. We started with the base Lorentz equation, set up a subtraction interval, applied the co-local condition to strip away spatial dimensions, and arrived at the final result,